Okay, so now we're going to go over lesson 17. Lesson 17 is on some concepts about graphs, about the shape of graphs. So this one, section 6.8, is about increasing and decreasing functions, and also covers a little bit about piecewise defined functions. All right, so what is an increasing function? If we have a function, we're going to say that the function is increasing over an interval AB if whenever you pick two numbers in that interval, any two numbers, let's say x1 and x2 in the interval, then you see you have this inequality, let's say x1 is to the left of x2, then when you apply the function pretty much respects the inequality. So it's like if the function is increasing, you can put f on both sides of this inequality, and the inequality would be respected. It will not be reversed. The inequality is preserved. So if you have any 2 points, x1 less than x2, if the function is increasing, you can put f on both sides, and it will be a true statement. Graphically, that means that if you take 2 points, now look at this graph, x1 and x2, x1 to the left of x2. Then when you plug them in, when you plug in x1 and f, you get f of x1. And the other one, which is to the right, when you plug it in f, you get something that is bigger. So f of x2 is bigger than f of x1, which is what we had there. So the graph is going to look like it's going up as you move from left to right. So graphically means the graph goes up. Algebraically means that you can apply f to both sides of an inequality, and the inequality will be respected. Okay, and decreasing is like the opposite. Things are reversed. So a function is going to be decreasing is if when you take two numbers, when you apply f on both sides of that, then things are reversed. You can write that as like this way. So you apply f on both sides of this, you're going to get f of x1 is bigger than f of x2. So the inequality is reversed, or you can write it like this. F of x1 is bigger, so you can write it like this if you want the inequality sign to point towards the left. But if you don't put it in this order, then you see when you apply f on both sides, if the function is decreasing, the inequality is reversed. And from the point of view of the graph, so f of x1, if x1 is bigger, f of x1 is bigger than the next one. When you apply x2, f of x2. F of x2 is smaller, which is what this inequality says. F of x2 is smaller than f of x1. And visually, it looks like the graph is decreasing, falling, when you move from left to right. Okay, so it is rather easy to do this visually to determine whether something is going up or down. If it goes up, it's increasing. If it goes down, it's decreasing. When you take calculus, you're going to learn how to do it algebraically. But in this class, we only concentrate on learning how to do it visually, so from the graph. All right, so if you have a random graph, you can always, even if the graph is not always increasing all the time or decreasing all the time, you can break it up into pieces where you can say, okay, in this piece it decreases, in this piece increases, and so on. So any graph, you can do that for any graph. So let's do that for this graph. This graph, okay, looks like a W. The question is, find the intervals in which this graph increases or decreases. Okay, so we're going to break it up. Note that in this piece right here, it is increases. This piece is decreases. On this piece, it goes down, so it decreases. After this point, it goes up again, so it increases. So we can classify each and every part of this graph like that. So let's write down the intervals where the graph is increasing. So the graph is increasing in this piece right here. Right, it goes up as you move from left to right on this piece, it goes up. So looking at the x coordinates, that means it goes up from -1 to x equals 0, so to 0. So you write here the x values. So between this piece and this piece, in this part, the graph is increasing. Also, it is increasing from this point onward, from 1 to infinity, assuming that the graph goes on forever. Or assuming that the graph goes on forever, it increases from 1 onwards, goes up. Now, on the pieces where the graph is decreasing, so let me now put that one, let's say, in purple. So in this piece, the graph decreases. So as you move from left to right, it goes down. So that would mean from minus infinity to -1. And it also decreases in this piece right here. This part goes down. So in this piece right here. So from 0 to 1. So on those intervals, it decreases. And that's it. By the way, it is not wrong to um, say to include the endpoints if there are no holes on the graph. So really, it is also correct because these two numbers are included. The graph actually starts decreasing from this point. It is not wrong to say that it is decreasing, including the 0 because there's no hole there, and including the 1 because there's no hole there. So both of these answers are correct. We're going to focus though on giving the answer in interval note, in open, like this, open intervals. So both are correct. We're going to give the answer like this though, in open intervals. Okay, so let's do another one of those. Now let's look at this graph and state the pieces on which it is, the intervals on which it is increasing and decreasing. Okay, so this one is going to be, to start with increasing, the graph goes up between -8 from here to here. So from here all the way to this part. And remember, we're looking at it from the point of view of the x. So from from -8 up to there. So in this whole part, the graph is increasing, goes up. And then also again from here to here, above this segment, the graph goes up. And then after 5, the graph goes up as well. After 5, it goes up again. So it is increasing in all these pieces. So in this part, so let me see. So the graph is increasing in this piece. The graph is increasing in this piece. And the graph is increasing in that part. Okay, so on all those three. So from the point of view of the domain, the x's, it will be from -8 to -2. And then from 0 to 2. And also from 5 to infinity, because after that, after 5, it doesn't go down ever again. The arrow indicates that that pattern continues forever. So it goes up forever after 5. So from 5 to infinity. and we give the intervals as a list uh, instead of as a union, is a list of all the places of all the pieces where the graph is increasing. That's how we usually give the answer in terms of a list of intervals, not a union. Okay. All right, and then for the pieces where the function is decreasing is basically the rest. So the function is decreasing. Remember, you're always moving from left to right. So this part, then you decreasing in this part, and you're decreasing in this part. So you are decreasing, the function is decreasing from minus infinity to -8. That's one interval where the function is decreasing. The function is also decreasing from -2 to 0, and the function is also decreasing from 2 to 5. Okay, and that is it. That's where the function is decreasing. These three parts, that, and that. By the way, it could happen that some pieces of the graph are neither increasing nor decreasing. So you might wonder how could that happen, neither increasing or decreasing? Well, functions that are constant or pieces that are constant then are considered to be neither increasing nor decreasing. So you could have a function, um, let's say that looks like this. Okay, then in this piece, the function is neither increasing nor decreasing. We say that in this piece, the function is constant. Okay, so in this piece, the function would be neither increasing nor decreasing, but constant. Okay, so constant functions are neither increasing or nor decreasing. Some people do include the possibility of less than or equal um, sign in this definition. In that case, constant functions would be both increasing and decreasing. Where we're using the definition for strictly increasing, so that means we do not allow for that. So we're just gonna call these parts constants. Okay, this is a constant uh, part of the graph. Okay, now the next concept that we have to talk about is the concept of piecewise defined functions. Now, this concept is pretty important. It is essential in computer programming. Like, if I don't know if you know a little bit about programming, then you'll have already encountered this concept. Or if you eventually want to learn some programming, you really need to get to this because this is how computers operate. So the concept of piecewise defined function is very, very similar to the concept of a flow chart. So this is a flow chart that I got from Wikipedia. He's basically saying like, okay, if they ask you a question, if the answer is yes, then you do this. If the answer is no, then you do that. So here's an example. So this is about what to do if a lamp is not working. So if a lamp is not working, question, um, is the lamp plugged in? If the answer is no, then you do this, which is plug it in. If the answer is yes, then okay. Is the bulb burned out? If the answer is yes, then you do that, replace the bulb. If the answer is no, then you do this, which is repair the bulb, repair the lamp or just buy a new one. Okay, so that's how piecewise defined functions work. It's basically, uh, it's like they ask you, is your X that you want to plug in, does your X satisfy this? If it is yes, then plug it in here. If it is no, then try another part. So it's very similar. So here's uh, the concept explained algebraically. So a piecewise defined function is just going to be a function in which more than one formula is used to define the output. And the output depends on what the input is. So you have an input, you have to ask yourself, does the input satisfy this property? If it is yes, then plug it in. If it is no, then check some other part. Um, each piece has its own domain, and the domain of the entire function, oops, that's a typo, and the domain of the function is a union of all these smaller domains. So here's the first example about piecewise defined functions. So piecewise defined functions look like this. So this is a function that has two defining formulas. It has two parts. You could have 3 parts or 4 parts. There's no limit to the number of parts. You could even have infinitely many parts. Uh, Most of the time in this class, we're just going to deal with 2 or 3 parts, but there's no reason why it has to be only 2 or 3. It could be way more. Okay, so you see, look at this. This has two formulas, and this formula, x minus 1, is if x, for the input, is less than or equal than 0. So basically, if I give you a number that is less than or equal than 0, then you're going to use this formula to figure out what is the output. And if your x is bigger than 0, then you're going to plug it in here to figure out the output. And that's basically all that it is. So, for example, let's plug in -1, then 0, and then 4. Figure out what those are. Okay, so first of all, let's plug in x equals -1. Okay, x equals -1, I have to figure out which of these conditions is satisfied. -1 is less than or equal than 0, so that means I'm going to plug it in this formula, the formula that says x minus 1. So that's where I plug it in. The other part, I ignore it. So I'm going to plug in -1. In this one, it says -1 minus 1. Plug it in the top. -1 minus 1 is -2. So that means f of -1 is -2. Okay, that's it. Now let's figure out what is the output of x equals 0. So plugging in f, plugging in x equals 0 in f. Again, you have to ask yourself, which of these two conditions does 0 satisfy? Is 0 bigger than 0? No. So that means it's not the bottom. Is 0 less than or equal than 0? Yes. So that means, again, we're going to use the top formula. So I'm going to plug in 0 in the top formula. So that means instead of x minus 1 is 0 minus 1. And 0 minus 1 is -1, simplifying. So f of 0 is -1. Okay, and then lastly, let's plug in x equals 4. We're going to figure out what f of 4 is. Well, is 4 less than or equal than 0? No, right? So then, check the next condition. Is 4 bigger than 0? Yes, so that means this is the formula where we have to plug in the 4. So I'm going to plug in the 4 here. So this is going to be 2 times 4 plus 1. And this is 8 plus 1, which is 9. So that means f of 4 equals 9. Okay, so that's how you figure out the outputs. Just see where it's supposed to go, and then plug it in the corresponding formula. Well, now we're going to graph this thing. So because there's 2 parts, the graph is also going to consist of 2 parts, 2 pieces. So the pieces could be um, separated like this. So you could have a graph that have like, let's say something like this, one piece, and then the other piece like that. So it could be split up. And it depends if you go all the way to infinity and like that, and then like that forever. So it could be separated, or maybe they're joined at that point. It could happen. That could happen as well, like this. All right, let's figure out what this one looks like. All right, so note that if I only had this formula, just the top, and nothing else, just the top, then that would be that would be a line. The graph of that would be a line. So that means the graph of this piece, which is the piece for all numbers less than or equal to 0, is going to look like a line that is just going to stop abruptly at 0. So it is a line all the way to the left until you hit 0. So that means we're just going to graph this line knowing that it ends at 0. So okay, so when you plug in 0, that's going to be the end coming from the left. When you plug in 0, you're going to get -1, which we already did it here. So when you plug in 0, you're going to get -1. Let's plug in 0, you get -1 right here. Okay, 0, -1. And 0 is included, so I'm drawing a filled in dot. Now, as I said, I know that to the left is going to look like a line. So all I need is just another point on the left of this, and I can connect those 2 points, and that's it. That's the line of the the graph of that was going to be the first part of this graph. So let's take another point. Let's say I plug in -3 or -4. Let's plug in -4. If I plug in oh, actually, I already plugged in a number to the left. I plug in -1. So if you plug in -1, you get -2. Let's use that one. That's even better. So if you plug in -1, you get -2. Plug in -1, you get -2. Okay, but you could have plugged in any other point. Let's say you can plug in -4. -4 minus 1 is -5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, you could have plugged in just another point. All right, then you plug it, you connect to those, and that's it. That's the graph of the upper piece. Is this line right there? Goes on forever. So that's the graph of the top piece. Now let's draw the graph of the lower piece. The graph of the lower piece, again, if I didn't have the top piece, the graph of that would be a line as well. That's going to be a line. But it's a line now, we're only going to need the part of the line for x bigger than 0. So that means the beginning of that line happens when x equals 0. You're not going to include the x equals 0 part because x equals 0 is not included in this piece, but if we were to include it, then it would start right at 0. So now what we're going to do to get the beginning is to plug in 0 on the second one. So if you plug in 0, you would get 1. So, but that's not included, right? So I'm going to draw a hole like that. I plug in 0, I get 1, but that's not included. Uh, x equals 0 is not part of that. Now, pick a number bigger than 0, any number you want, but we already used 4, so I'm going to use that one. Plug it in this part, just like we did there, and we get 9. So that means when I plug in 4, I get 9. 1, 2, 3, 4, 9. Again, you could have used any other point. I'm just using the one that I already computed. Then this piece, the graph of this part is a line, and that's the graph of the lower piece. So those are the two pieces for this graph. That's the graph of this piecewise defined function. Okay, now I'd like to do two more examples. of how to graph piecewise defined functions. Example 4 is going to have 2 pieces, and then example 5 is going to have 3 pieces. Okay, so let's sketch this one. Note that this one is broken up right at 2. So all the numbers from minus infinity up to 2, 2 is not included. And then all the numbers from 2 and bigger, so from 2 to infinity, and 2 is not included either. So 2 is not included in either one of them. And also note that both pieces, if I were to graph any one of them individually, that's a line, and the one on the bottom is also would be the graph of a line as well. But they're cut short. So this line, I'm only going to take the part from minus infinity all the way to 2. And for this one, I'm going to take the part from 2 to infinity. All right, so both are going to be lines, and I want to start by knowing where do they stop and where do they begin. So the top one starts from minus infinity and stops when x equals 2. So right at x equals 2, what do we get when we plug in x equals 2? That's going to be the end. It's not going to be part of the graph. I'm not going to include it, but I need to know where it stops. So when plug in x equals 2, when you plug in x equals 2, 2 times a half is 1, and 1 minus 1 is 0. So if you were to plug in 2 at the top, you would get 0. So over 2, you get 0. It's not part of it, so you have to do it as a hollow dot. Okay? Alright. Now, grab a number to the left of x equals 2. Let's say I'm going to grab x equals negative 2. Okay, so if I plug in x equals negative 2, which satisfies this property, I'm going to plug in negative 2 on the top here. So 1 half times negative 2 is negative 1. Negative 1 minus 1 is negative 2. So when x equals negative 2, you get negative 2. That's included. Okay, so then you connect these two, and that's the graph of the upper part of this piecewise defined function. Okay, that's the graph of the upper part, this part. Now, let's draw the graph of the lower part for all x is bigger than 2. Okay, that's a line, and let's figure out where it begins. It would begin when x equals 2. That beginning is not included, but we need to figure out what is the beginning, if it were included. So plug in x equals 2 in this part. If I plug in x equals 2 in here, I would get negative 3 halves times 2. You can put that in a calculator. That's negative 3. And then negative 3 plus 1 is negative 2. So when I plug in 2 in the lower part, I get negative 2. And that's not included. So hollow dot. When you plug in 2, you get negative 2. Okay, now I need a number to the right of 2. Let's say I pick 6. No, something smaller. 4. Let's say you plug in 4. So if you say negative 3 halves times 4 plus 1, that is negative 5. I just put that in a calculator. You get negative 5. So when x equals 4, 1, 2, 3, 4, you get negative 5. 1, 2, 3, 4, 5. Okay, when you plug in 4, you get negative 5. Connect those two dots, and that's the graph of the lower part. There you go. There's a huge dot. Okay, I didn't mean to draw it that big, but okay. That's it. That's the graph of that piecewise defined function. Now let's draw the graph of the last one. Okay, this one has three pieces. Okay, first piece is from minus infinity to 1, then the middle piece is from 1 to 3, including the 1 but not the 3, and then the next one from 3 to infinity, including the 3. Okay, so let's note that again, I'm making all these ones easy, so all of them are going to be just like lines, uh, not too complicated. As long as you understand the concept, that's what matters. All right, so let's start with the top piece, the top part, which is on the graph is the leftmost part. Okay, so it's going to be a line, and it's going to stop right at 1. So it goes from minus infinity to x equals 1. If you plug in 1 in the top formula, which is not, x is not included, if you were going to plug in 1 proper, it really should be on the middle piece. But just to figure out where this line stops, we're going to plug it in the top. Okay, but it's not going to be part of the graph because you're not allowed to plug it in the top. It should be on the middle one. All right, so plugging in x equals 1, you get 1. So at 1, you get 1. Not included, so there. And now grab a number to the left of that. Let's say negative 4. Negative 4, that is in this interval proper, so you plug it in there, you get negative 4. So negative 4, 1, 2, 3, 4, 1, 2, 3, 4, that one. Connect these two dots, and that's the graph for the top part. Okay, now let's draw the graph for the middle part. The middle part is starts at 1 and ends at 3. The one part you do include is x equals 3 part you do not include. Okay, so let's see where it begins. Plug in 1. If I plug in 1 here, I will get 3. So when I plug in 1, I will get 3. Plug in 1, 1, 2, 3, 1, 2, 3. That is included, so fill in dot. Now plug in x equals 3 to see where it ends. It's a line. It's going to be a piece of a line, segment. So 1, 2, 3, plug in 3 in the middle formula. You get 7. 1, 2, 3, 4, 5, 6, 7. And that one is not included. Remember, that one is not included. Connect these two dots, and that's the graph for the middle piece. Okay, that's the graph for the middle piece. And now the graph of the last part for x bigger than 3 all the way to infinity. So it starts at 3. When x equals 3, 1, 2, 3. When x equals 3, you get 1. And for any other x after that, let's say 5, you also get 1. It's a constant. So 5, you get 1. Okay, connect to those two, and that goes on forever. That's the graph of the third part, which is the rightmost part. Okay, and that is the graph of that piecewise defined function. Okay, another concept that is important to talk about regarding functions and their graphs is the concept of symmetry, which is encoded in the concepts of even and odd. These are the the two most important types of symmetry a function can have. And first, the function of even. So we're going to say a function is even, or is an even function, if whenever you plug in, for any x, whenever you plug in, let's say negative x, you end up with exactly the same thing as if you had just plugged in x. So plugging in, for example, let's say a particular number like -5, if the function is even, then plugging in -5 is exactly the same thing as plugging 5. So one really quick and easy example of a function that is even is the squaring function. Because if you plug in 5, you get +25, and if you plug in -5, you still get also +25. So plugging in -5 in the squaring function is exactly the same thing as plugging in 5. The output is exactly the same. It makes no difference whatsoever in the output. You get exactly the same answer. So that is the concept of even. If you plug in the negative counterpart of an input, you get exactly the same thing as if you had not put in that negative number, that negative sign. Makes no difference. So f of -x is exactly the same thing as f of x. So that's what it means algebraically. In terms of graph, a function is said to be even if the graph, when you look at the side that is to the right of the y-axis, then the side that is to the left of the y-axis is a mirror image, like a reflection of that one. Okay, so the side that is to the left of the y-axis is the mirror image of the side that is to the right of the y-axis. So it's basically symmetric about the y-axis. So even or symmetric about the y-axis. So from the formula, the way you can figure out whether a function is even or not is you plug in -x, you simplify all the way as much as you can. If you end up with f of x, then the function is even. That's how you do it algebraically. If you have the graph in front of you, the way you figure out whether the function is even or not is by looking at the graph. If the right-hand side is the image of the left-hand side, then the graph is even. Okay, so that is the concept of even. The concept of odd means that if you plug in -x and you simplify, you end up with negative f of x. All right, so that's odd. So odd would be if I plug in -x and I simplify as much as I can, I end up not with f of x, but negative f of x. And that's algebraically. And then from the graph, odd would mean that, let's say I have that piece. The other part, if the graph is odd, if the function is odd, the graph is going to look like, let's say I have one piece on the first quadrant, the other piece is going to be on the third quadrant. There's not going to be anything in the second and fourth. And this part right here is going to be, it's going to be like a double reflection. If you were to first reflect this across the y-axis, so the mirror image, and then you do the mirror image again, but now with respect to the y-axis. So it's like a double reflection. You reflect and then reflect down. First reflect sideways and then from top to bottom. So it's a double reflection. First here and then down there. So that would be odd. That would be symmetric. We say that that's symmetric about the origin. But again, it's like a double reflection. Reflect first like this, and then that reflected down. Okay, that is the concept of an odd function. There's one third way you could explain this is by saying that if you have a point on the graph for even, then if this is a point on the graph and the graph is even, then negative xy is there. So for example, let's say I have a point here on this graph. If this, my function is even, then the point that has coordinates negative x, y is also on the graph. Same height, so same y, and then the x is on the opposite side, so negative x. And then if the function is odd, you have a point right here, let's say x comma y. If the function is odd, then the point that has coordinates both negatives is going to be negative y, negative x, negative y is also going to be on the graph. Alright, so let's do some of these algebraically. Algebraically is harder, so we're going to do more examples like that, and then visually, graphically is just very easy. Is it a reflection or not? Okay, so let's start with these. So question, let's figure out whether this function is even or odd or neither. It could happen that a function is neither. Okay, so how do you do this? So whether it's even or odd, you do it exactly the same way. You first have to plug in f of negative x in the formula. And then you're going to simplify as much as you can, blah, 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 blah. If when you simplify, you end up with f of x, the function is even. If when you simplify all the way, you end up with negative f of x, the function is odd. If you do not end up with either of these, then the result is the function is neither. Okay, so, but regardless, you always start off the same way. Plug in negative x and simplify. So plugging in negative x in the formula, you would get negative x cubed plus negative x to the fifth. Simplify this. This is negative x cubed. When you have a negative sign raised to odd power, you end up with a negative sign. When you have a negative sign raised to an even power, you end up with positive. For example, negative 1 squared, that's raised to an even power, that's 1. But negative 1 cubed, that's negative 1 times negative 1 times negative 1, you end up with negative 1. So whenever you raise a negative sign number to an even power, you end up with positive. Whenever you raise it to an odd power, you end up with negative. So that's why here, raising negative x to the third gives me negative x to the third because there's an odd power. So if you start with negative, you're going to end up with negative. And similarly, this is going to be negative x to the fifth. Now, our job is to compare. That is not the same as f of x, right? This is not the same as f of x, so that means this is not even, but it could still be odd. So let's check. Okay, it is for sure not f of x, it is not even, but we still have to check against the negative f of x. So factor out the negative. If you factor out the negative, you end up with x cubed plus x to the fifth. And note that what is inside the parentheses These parentheses is actually f of x, so that means this is negative, the negative outside, and this is actually f of x. So that means when I plug in negative x, I end up with negative f of x. So that means the function is odd. So the function is odd. The function is odd. Okay, let's try another one. Let's figure out whether this is even or odd. So we start out the same way. Plug in negative x. Then we're going to simplify this as much as we can and compare. So negative x replaced here will be negative x squared minus absolute value of negative x. Wherever I see x, I replace it with negative x. And then we're supposed to simplify this as much as we can. Negative x squared, I'm raising it to an even power, so it's going to be positive, so it's going to be x squared. And then the absolute value of a negative number is the same thing as taking the absolute value of the positive number. So this is going to be the same as absolute value of x. What I'm saying here is taking the absolute value of a number is the same as taking the absolute value of a negative number. So the absolute value of negative x is the same thing as the absolute value of x. There's no difference whatsoever. So I can say that the absolute value of negative x is the same as the absolute value of x. And now comparing, this is actually the same thing as f of x. So, because we ended up with f of x, that means the function is even. Okay, that function was even. Okay, now that I've done two examples, I think you should stop the video, pause it, and try that one on your own before continuing. So it says, figure out whether f of x equals x cubed minus x squared. All right, let's see. Uh, Start out the same way. Plug in negative x and see what you get at the end after simplifying. So plugging in negative x, you're going to end up with negative x cubed minus negative x squared. Then simplifying, this is an odd power. So when you raise negative x to the odd power, you're going to get a negative x cubed. And then this one, negative x to the even power, there's going to be positive x squared. This minus is that minus, but then this becomes the x squared. So you end up with that. Okay, and then comparing, this is neither f of x, it is not f of x, they're not the same thing, right? This one is positive x cubed, this one is negative x cubed, it's not the same thing. And then if you pull out a negative, you end up with x cubed plus x squared, which is not negative f of x either. This inside right here is not f of x. So this is not negative f of x. So the function is not even, and is not odd either. So we compare it against f of x, they're not the same. We compare it against negative f of x, they're not the same either. So the function is neither even nor odd. So neither even nor odd. All that means in terms of the graph is that the graph is not symmetric. It's not symmetric with respect to the y-axis, and it's not symmetric with respect to the origin. So there's no symmetry um, there. That's all. All right, let's do a couple more. Find it. Okay, here's another one. If you didn't try the previous one, you should definitely try this one and the next one. So pause the video and try them. And when you're done, follow here. Okay, let's try this one. Plug in negative x and let's simplify as much as we can. This is 7 minus negative x squared minus negative x to the 6th. Okay, this is raised to an even power, so this is going to be just x squared. This is raised to an even power, so it's also going to be x to the 6th, and those minuses are the ones that were already there to begin with. And note that this is actually comparing against f of x. It is exactly the same thing as f of x. And this means that this is even. In terms of the graph, that means that the graph is symmetric with respect to the y-axis. So the right-hand side of the y-axis is a mirror image of the left-hand side, the side that is left to the y-axis. Okay, now let's do this one. Now let's plug in negative x, because that's how we always start it, regardless of whether we're looking for whether it's even or odd. Plug in negative x, so negative x squared plus 1 over negative x. This is x squared is raised to an even power plus 1 over negative x. If you can, we cannot simplify much. I mean, much more. Maybe we can move that negative around, but there's not much to do. Let's see. Comparing to f of x is not exactly the same. This is not f of x, so that means it is not even. But we can move that negative. We can put it right in front. It's really the same thing. So moving it to right in front, this is going to be x squared plus 1 over x. Now when you write it like that, though, this is exactly the same as f of x. So this is negative f of x. And because it is negative f of x, that means the function is odd. Okay, it is odd. Okay, and here's the last one. One where you can just tell whether it's even or odd by looking at it, or neither. Let's look at this. Zoom in a little bit. Let's look at the graph of that. That's the y-axis. Note that the right-hand side really does look like a mirror image of the left-hand side, and it is. Just analyze it carefully. It really is a perfect mirror image. The right-hand side is a perfect mirror image of the left. So that means this is even. Okay, so that pretty much completes lesson 17. There's only a couple of things I need to mention. There's a bunch of what we call basic functions that you need to be familiar with because they appear over and over and over again, not only college algebra but also in other math classes, such as I don't know, pre-calc in calculus. And they're called, some books call them the toolkit functions or the parent functions. They are used a lot for examples. When you want to think of an example of something, some of these graphs are very useful for that. And you should just be familiar with them. So whenever you see a function, if you know the parent function, you already have like a visual in your mind of what the graph is going to look like. So a function that is a constant function, all of them look like this. They're horizontal. So maybe it's a little higher up or a little lower down on the xy plane, but they all look the same. They're all horizontal. So constant functions look like horizontal lines. Uh, the basic function f of x equals x or y equals x it looks like a line, and it perfectly divides the first and fourth quadrant in halves. Okay, so that is y equals x or f of x equals x. The graph of the absolute value function looks like a V. Note that this is even. If you plug in, if you plug in negative x, you get the absolute value of negative x, but this is the same as absolute value of x, which is the same as f of x. This function is even. The right-hand side is a perfect mirror image of the left-hand side. So the absolute value function, the graph of the absolute value function looks like a V with the vertex right at 0. Okay, the next example of a basic function, and we're going to focus on this in a little while. This is a squaring function. We call the graph of that a parabola, and it is also perfectly symmetrical, just like the absolute value function, but it's more curvy. It looks like that. Okay, and it goes on forever. There's no reason to stop there. Okay, so it is also even. We explained why before. When you square a negative number or a positive number, um, like negative 5 and 5, you get the same thing. So f of x, this is also even. F of negative x is the same, plugging in negative x is the same as plugging in x. Alright, so the graph of the x equals squared, and that's the basic image you should have in your head when you think of that. The cubic function looks like this. The graph of the basic cubic function. This one is odd because when you plug in negative x, you get negative x cubed. And simplifying this, you're raising it to an odd power. So this is negative x cubed, which is negative f of x. This one is odd. Okay, and if you look at the image of the graph, the piece in the first quadrant is a double reflection of the piece in the third. So if you reflect to the second and then from the second to the third, you get mirror images. We call that symmetry about the origin. Okay, so that one is odd. The graph of 1 over x looks like this. The graph of 1 over x squared looks like that. The graph of the absolute value of x, this one is even, by the way. And this one is odd. You can check by plugging in the formula and simplifying, negative x. The graph of square root of x, this is neither even nor odd, but it looks like this. It's basically half of a parabola that is sideways. Uh, so if you had a parabola that looks like that is sideways on its side, the graph of the squaring function, the graph of y equals x squared, put it on its side, then the top part, which represents taking square roots of positive numbers, because taking square root of negative numbers gives you imaginary numbers. The top part is the squared function. Okay, so it's like half of a parabola, and it goes on forever. This is neither even nor odd. And then the cubic one is similar to the cubic, but again, it's on its side, and this is odd. You can see from the graph, this piece is double reflection of that one. Reflect across the y-axis and then reflect across the x-axis. So that one is odd. So those are the basic ones. The most important of all of them are one, constant functions. You should know that constant functions look like horizontal lines. This one, you should know what 3 and 4, the absolute value of the graph of the absolute value function and the graph of the squaring function. That's parabola. We're going to talk more about those. Then 5. For now, these ones 6, 7 are not as important. But then 8 is also pretty important. Okay, so the ones I have circled are really the most important ones. Well, all of them are kind of basic, but okay, and that concludes that lesson. Just become familiar with those so that whenever you see this, you have an idea of what the graph looks like. Okay, that's it.